Now, if you remember where we're at, so we're talking about a very specific type of differential equation. So there's lots of adjectives here describing it. It's a linear, it's homogeneous, it has constant coefficients. So all of these things come together means that we have a differential equation that looks like this. Some derivative plus the constant times another derivative plus the constant times another derivative and so forth and so on equals 0. The equals 0, that's the homogeneous part. And we said, okay, these are the differential equations that we like, because when it comes to solving differential equations, especially linear differential equations, there's essentially two steps to solving linear differential equations, which is, find your n linearly independent solutions and then figure out the right linear combination to take. Finding the right linear combination is not so bad. Finding your n solutions takes work. But we said in this special case where we have these constant coefficients, we can transform the problem. So that is, we go from the differential equation problem, and remember this stands for ordinary differential equation, and we transform it into what we call the characteristic equation or auxiliary equation. So this is just terminology. So if you see something that says, hey, here's the characteristic equation, or here's the auxiliary equation, this is what it's talking about. It's a very easy transformation. You can just see derivatives become the right powers, right? So third derivative, r cubed. Second derivative, r squared, so 3r squared. First derivative becomes r, so minus 7r. No derivative is like to the 0th power, so that becomes a constant. So we transform a derivative into a polynomial. Now, this polynomial, what do we care about? We care about the roots. Find the roots. And I think there was a question. I may have seen yes.
What happens if then the ordinary differential equation is like just a plus 5 at the end with no y term?
So if there's a plus 5 on the end with no y term, either somebody made a mistake and forgot to write it down, which I've done before, or what you do is you move to the other side and you have something that's non-homogeneous. So if it's just a plus 5, that makes it into a non-homogeneous. So either somebody had a typo or it's a non-homogeneous equation. And we haven't talked about non-homogeneous yet. We'll mention it in our next session. And after our exam, we're going to get into it and like, okay, here's how you deal with some special cases of solving non-homogeneous problems. So that'll be something to look forward to in the near future. All right. Now, the other thing we talked about at the very end, and because, oftentimes when we're at the very end, we're so excited to leave the room, we're like packing stuff in our bags, and we may have forgotten to actually write this down. So suppose we have our roots, and there's some root, alpha, that's a repeated root. And you might say, well, isn't every root repeated? I mean, sure, sometimes it's just repeated once. Okay, but let's say it's repeated multiple times, k times. Now, we have to think about what to do. Because when we have a root, what really comes out is that a solution to our differential equation is e to the power alpha x. That's what a root does. It gives us a solution. But I can't say, oh, here's e to the alpha x, and here's e to the alpha x again, because the second time I show it to you, you're like, wait a second, I've already seen this. You haven't given me anything new. You haven't given me anything fundamentally different than what you have already. So we need to do something to it. So the way we do something is bump it up. And how do you bump it up? You work through powers of x in front. So the first root will be e to the alpha x. The second, add an x in front, x e to the alpha x. The next one, x squared, and so forth and so on. So that's what we do if we have repeated roots. That's the rule. Now, let's do an example. Find the general form for solutions of the following. So you have 3y, what's this notation here? 7th derivative. Now, if you think about it, it's like, whoa, hold on. We've only ever done something on a second derivative problem. And now we're jumping all the way up to 7th? Aren't we like skipping 3, 4, 5, and 6? Yes. Yes, we can, because we have the technology. This is how strong this technique is. We can handle 7th derivative problems. Okay, so 3 times the 7th derivative of y, minus 11 times the 6th derivative of y, 13 times the 5th derivative of y, minus 5 times the 4th derivative of y equals 0. And we want to find the general form. before we start, how many linearly independent functions are we going to need to find? Seven. So whatever the highest derivative is, that's how many functions need to come out. So we need 7 linearly independent solutions. Now, let's think about it. First step is we transform our differential equation into our characteristic equation. So in other words, to the algebra we go. So what's the characteristic equation going to be? 3r to the 7th, yes. 11r to the 6th, yes. 13r to the 5th, we're on a roll. Minus 5r to the 4th equals 0. Now, hopefully you can see how this works. You say, hey, if I see the 5th derivative, that's r to the 5th, and so forth and so on. So this should be an automatic step. There should be almost no thinking involved, which is good. That's one of our goals. We have to think as little as possible, because the more we think, the more likely we get into danger of making a mistake. All right. And now we want to find the roots. And we should point out, r to the 7th means this is a 7th degree polynomial. It means that there are 7 roots to find. Okay. So, how do we go about finding our roots? I feel like this is like an advertisement for something like Ancestry.com. Find your roots on Ancestry.com. No, that's not the kind of roots we're talking about. What do we do? Yeah, we can factor a little bit out. And we'll say, okay, r to the 4th. Pull that out. That's easy to do. So we'll have 3r cubed minus 11r squared plus 13r minus 5. And we see these roots are going to be easy. R to the 4th, what roots are we getting from here? 0. And we're going to get it 4 times. So 0, 0, 0, and 0. Okay, now we're down to just a cubic. Well, that's great. Can we use the quadratic formula here? No, because it's not a quadratic, it's a cubic. You might say, well, maybe we can use the formula for cubic. There is one. Do you know it? Yeah, so we can't use it then. All right. So that's out. So what can we do? All right. So there's a very ancient method in mathematics that helps us to keep going. It's been passed down from thousands of generations. Back when they did math by looking at, rocks, and they're like, one rock, And that method is called guess. It's a powerful mathematical method which says, okay, if I don't know any roots, I'll guess a root. Now, I might guess wrong. That's okay. But at least we're making progress. Because a wrong guess says, well, at least it's not that one, only infinitely many more options to go. But we can guess very smartly. Okay, so what's a good guess? Wow, okay, you guys are really jumping ahead of me here. I was going to point out a good guess in general. So in general, there's a nice rule that says you look at the last number and the first number. In other words, the leading coefficient, the last coefficient. And what you do for your guesses is if there's any nice number, it's going to take the form plus or minus a factor of your last digit. So I'll say it's a factor of 5. Divided by a factor, I can spell factor, of your leading digit, leading coefficient, I should say. So, in other words, either at 1 or 5 on the top, or 1 and 3 on the bottom. So this says you could have 1, -1, a third, -1/3, 5, -5, 5/3, or -5/3. Those are the only nice roots that are possible. So these are the guesses we make. Now somebody said 1. That's a great guess. In fact, it's a wonderful guess in a math class because oftentimes mathematicians are addicted to zeros and ones. We like them. So how do we check 1? We've made our guess. How do we know if 1 works or not? Plug it in. Okay, so let's plug in 1. 3 minus 11 plus 13 minus 5. Well, think of it as 3 plus 13, which is 16. Then we're going to subtract 11 plus 5. 11 plus 5 is 16. 16 minus 16. Oh, it works. We found a root. Our guess method has come in to save us. Okay, great. So we know that 1 is a root. Now, what does that tell us? It tells us that our polynomial is r to the 4th. Because 1 is a root, that says r minus your root is a factor. And then there's other stuff. How do you get the other stuff? Yeah, long division. Oh, man, this feels good. It feels like we're going back to our 8th grade. We're in algebra class, and we're like, look at us. We still remember this stuff. We're good. Okay, so we're going to divide r minus 1 into the polynomial we started with, which is 3r cubed minus 11r squared plus 13r minus 5. Now, in case you don't remember it, we'll do a quick recap. And here's how long division works. Just focus on the leading terms at every step. So here the leading terms are r and 3r cubed. What do I have to multiply r by to get 3r cubed? 3r squared. All right, so I put 3r squared. Now, I'm going to multiply 3r squared by the whole r minus 1. So that would be 3r cubed minus 3r squared. And then I'm going to subtract off, because I say, look, because of the 3r squared, I already have that accounted for. And so the question is, well, what haven't I accounted for? Well, the 3r cubes cancel by design. Minus 11r squared minus minus makes plus 3r squared becomes minus 8r squared. And everything else just comes down. All right. Now leading terms again. What do I have to multiply r by to get to minus 8r squared? Negative 8r. Yeah. See, this sounds like not hard stuff, right? And the answer is, yeah, you're right. It's not hard stuff. Just focus on step by step. Be patient. Okay, now we multiply negative 8r times this whole thing. So negative 8r squared. Negative 1 times negative 8r is plus 8r, subtract. The 8r squareds cancel. 13r subtract 8r. 5r. And then minus 5 comes down. What do I have to multiply r by to get to 5r? By 5. So then I multiply 5 by the whole expression, r minus 1. 5r minus 5. Subtract, what do I end up with? 0, which means I'm done. Now, what would happen if I got to the end and it wasn't 0? It means you made a mistake, which means you go back and check your work. Because you get a 0 if you definitely had a root. So either we didn't really have a root, we made a mistake there, or we made a mistake in our computation. But we got 0, so we're good to go. All right, so the good news is, by guessing a root, we were able to get down to quadratic. Now, what do we do here? Sorry, what? Factor? Do you see how it factors? Of course, you can always say, guess again. Is there any good guess that works?
5 over 3.
Is there an easier guess that works? 1. 3 minus 8 plus 5 is 0. Now, of course, we could also just factor. That leaves us with just one last thing to go. We can actually reason out what it should be. So it's r times what's in front should give us 3r squared. So r times this is 3r squared. So what's in front? 3r. Now, you might say, okay, but how do I get the other part? Well, you say minus 1 times the thing on the end needs to give us plus 5. So minus 5. So that works when you are to a quadratic. You could do long division again. But, one example of long division, and it's like, yes, it's like riding a bicycle. It comes back. Okay, so let's write down our roots. We have 0, 0, 0, 0. I'm just writing it because we have 4 times. That's r to the 4th. What else? 1, 1, because it's repeated twice, and 5/3. Okay, so we've made great progress. So just to recap where we're at in the process. So we start the process with a differential equation of the right type. We turn it into this characteristic equation, which means it becomes a polynomial. We find the roots. The last step is to say, now that we know the roots, we write down the functions. And once we have the functions, we take the right linear combination. So we start with the function. So let's start with this 0, this first 0. The root of 0 corresponds to what function? Well, it would be e to the 0x, also known as 1. Now, the next 0 will be what function? X, because it's a repeated root, so you have to multiply by x. The next 0 will be what function? X squared. You got to keep bumping up, because we already had 1, we have x, so it'll be x squared. The next 0, x cubed. So normally 0 would just correspond to 1. So, but I can't have 1, 1, 1, 1. That's not 4 different functions. It's just the same function repeated 4 times. So we say, okay, 1, bump it, x, bump again, x squared, bump again, x cubed. Okay, what's the next function going to be? E to the x, as we're to our next root, which is 1. So our next function is e to the x. What's our next one? X e to the x, because we have a repeated root. What's our next function? E to the 5/3 x. So we have that the 4 roots, 0, 0, 0, correspond to the first 4 functions, and then the 2 roots, 1, 1, correspond to the next 2 functions, and the last root of 5/3 is the last function. Now, we're not quite done yet, but we're basically are. We just need to do what to finish up? Yeah, we need to put into the general form, just means add some constants. So we have c1 times 1 plus c2 times x, c3 times x squared, c4 times x cubed, c5 e to the x, c6 x e to the x, and c7. So we have 7 functions. And like we said at the start, we should expect 7 functions. It's the 7th derivative. And that's the answer. Done. Done. Now we've solved the 7th order differential equation. Wow. We're good. We're good. Okay, any questions? Yes?
Why is the equal sign like equal to something?
You're probably right. I should say equals y. Yeah. We can now throw a box around it. It's in a box. It must be true. Okay, so let's go to our next thing. And there's a nice little fact here, which I don't know if it has any relevance to our example that we're about to talk about, but the fact is about the following. So there's this number called I, and I is defined by saying, well, if you square it, you get -1. Sometimes it's called imaginary. You know, I has a rough life. Everyone thinks it's just imaginary, but all right, well, we'll go with that convention. And there's this really interesting fact that says if you take e to the power I theta, and this is for any choice of theta, this is equal to cosine theta plus I times sine of theta. And this can be proved using calculus techniques. And so in particular, if you took calculus 2, and you remember we talked about series solutions, and so you can take the series function for e to the x and plug in I theta, and then you say, oh, if you just carefully rearrange the terms, out comes the series cosine theta plus I times the series for sine theta, and you get this relationship. Okay, so we're just going to take this as a fact. Now there's a fun little thing that comes because of this. If you multiply, e to the I pi and add 1, do you know what you get? You get 0. Yeah, this is a very famous equation because it involves e and I and pi, 0 and 1, addition and equals. These are all the cool math symbols hanging out together. It's quite a fun equation. Okay, so what does this fact say? So the fact, I'll rewrite it here, just so we'll do it in slow motion. It says, suppose you have e to the power a plus bi times x. Now, what you can imagine doing is you can think, well, I can distribute the x through. So this is e to the ax plus bx times I. And this plus sign, well, that's the same as e to the ax times e to the bx times I. And now you say, well, we know something about when we have I times something. So this becomes e to the power ax times cosine b times x plus I sine of b times x. So this is what the fact says. Okay, so we'll keep that in mind as we proceed with this next example. So find the general form for solutions of y double prime minus 4y prime plus 13y equals 0. Also, find the particular solution where y of 0 equals something and y prime of 0 equals something. So let's fill in the boxes. What do you want in the first box? 8. Wow, that was someone was just like, I've been waiting for this day. I'm ready for it next time you ask. 8. Okay, what's going in the second box? 6. All right. Okay, so hopefully we'll actually be able to fill this in. We'll solve, maybe. Okay, so here we go. So we have a differential equation of the right kind. Constant coefficients, linear, homogeneous. What's our first step? Characteristic polynomial, or you can just say, turn it to algebra, Steve. What's the polynomial? R squared minus 4r plus 13 equals 0. All right. Great. Now, what do we do next? We can try to factor it. Does it factor nicely? No, at least we don't see it. Sometimes it might factor, we just don't see it. That's okay, because we have other tools. Okay, someone said quadratic formula. R equals negative b, so that would be a 4. Plus or minus the square root of b squared, 16. Minus 4 times 1 times 13. What's 4 times 13? 52. You might say, well, that sounds like the number of number of cards in a deck. Well, yeah, there's 4 different suits, 13 cards in each suit, 52 cards. All over? 2a, which will be 2. Okay, so let's talk about 16 subtract 52. What is 16 subtract 52? Negative 36. That sounds like a nice number, at least the 36 part. What is the square root of negative 36? 6i. So we end up with 2 plus or minus 3i. Now the good news is, are these repeated or distinct? They're distinct, because one is 2 plus 3i, one is 2 minus 3i. Different numbers. So we don't have to do our like, aha, there's no bumping involved. Fantastic. Fantastic. So now we say, check this out. Check, 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 check this out. We can say that our solution looks like some constant e to the first root, let's say that's 2 plus 3i times x, plus some other constant times the second root, 2 minus 3i times x. And that's a true statement, but not a satisfying one. What don't we like about this? Yeah, we've got these 2 little eyes staring at us into our souls, saying, I don't belong here. Look at our original equation. There was nothing imaginary about that. Why should we have imaginary numbers showing up? So we say, okay, well maybe there's another way to write this. Okay, well let's think about it. If only we had a nice fact that would allow us to rewrite something that looks like e to the 2 plus 3I times x. If only we had something nice to help us.
That stinks.
Yeah, I know. Wouldn't it be great? Oh, hey, wait, I think this works. Right? Yeah, it's exactly this. Well, thank goodness we talked about it. Okay, so we have, so our first constant will be, so the 2 is the real number, so that's e to the 2x. And then the 3 times I, so that becomes cosine 3x plus I sine 3x. Okay, so that's, okay, so there we go. And then there's the C2. Yeah, we got that. Okay, now we still have the e to the 2x. And, okay, cosine of what? Negative 3x. But what's true about cosine of negative 3x? It's the same thing as cosine of 3x. Yeah, that's nice. So I can write it as cosine 3x. And then there's this other term. Okay, so then we're going to have sine of negative 3x. But wait a second. Sine. It's a very peculiar function. Very strange. Weird. Unusual. Some people might even say that sine is odd. Okay, so sine of negative 3x becomes negative. So the negative comes out of the sine function. So minus I sine 3x. And now you're looking at me and saying, Steve, you didn't solve the problem. You still have these two eyes staring deep into your soul. That's okay, we're not done yet. What can we do now? Well, we notice we have e to the 2x cosine 3x. And we have e to the 2x cosine 3x. Let's put them together. Okay, so if I combine my e to the 2x cosine 3x's together, how many do I have? What goes in front here? C1 plus C2. Right, I have a C1 here and a C2 there. What else can I do? Well, the other thing is I say, hey, I have e to 2x sine 3x. And that shows up in a couple places. Let's gather those together. What goes in front of that? It'll be C1 minus C2. And then there's a suspicious gap here. What? You, yeah, you what? Oh, I as the letter I. Oh, I thought you were saying, I'm thinking about this. I need a second to process. Okay. Common mistake. Okay. Now our grade. Oh! What's true about C1 and C2? They're numbers. We call them constants. So if I add two constants together, what do I get? Let's call it a new name. It's become a new constant, D1. What about C1 minus C2 times I? It's a constant too. So make that a new name, D2. And now we're like, wow, check it out. So this has become D1 e to the 2x cosine of 3x plus D2 e to the 2x sine of 3x. And now everything's real. There's no more i's. And you might say, well, where did they end up? Well, they got absorbed into the constants. That's where they ended up. They ended up inside of our D1 and our D2. But we didn't cheat. Everything here is legal that we did. Okay, so this is, remember this here is y. All right, so now we have the general form. So that means we found the general form. Check for that part. What do we need to do next? Find our particular solution. Okay, so we have y. To do our particular solution, we'll need y prime. Because we plug 0 into y prime. All right, what's the derivative of e to the 2x times cosine 3x? Two e to the 2x cosine 3x. We're using the product rule, so we take, there's going to be a derivative of the first part, leave the second part alone. What else do we have? Minus 3 e to the 2x times sine of 3x. The derivative of cosine is negative sine. That's where the negative comes from. The 3 comes from the chain rule, rid of the inside. Plus d2. All right, derivative of e to the 2x sine 3x. Two e to the 2x sine 3x plus 3e2x cosine 3x. Okay, now we plug in our initial conditions. Y of 0. So when we plug 0 into here, what comes out? 8 comes out, yes, but what else comes out in terms of d1 and d2? E to the 0 is? Cosine of 0 is? 1, so that says we have d1. E to the 0 is? Still 1. Sine of 0 is? So that goes away. So we have y of 0 equals 8 equals d1, which is great. That means we've solved for one of our constants. Okay, y prime is 0. Well, okay, equals 6, yes. What else? Well, anything with the sine goes away. The part with the cosine doesn't. So what do we have with d1? 2d1. What do we have with the d2? 3d2. Okay, so it's easy to solve for d1 because we say, there it is. That's the best kind of equation. That's the answer. Okay, for d2, well, we know d1. So we can say, for instance, 16, which is 2 times 8, plus 3 times d2 equals 6. So what does d2 equal? Yeah, subtract 16, divide by 3, negative 10 over 3. Negative 10 thirds. Okay, great. So our final answer is y equals d1, 8, e to the 2x, cosine 3x, minus 10 thirds, e to the 2x, sine of 3x. All right. Now, there's a space left here. That's not for part of our problem. This is just for a general statement. So if we have roots, a plus or minus bi. So it should be noted that one of the things we know from algebra is that when we have roots of a polynomial, and if all the coefficients are real, if we ever have complex roots, they occur in conjugate pairs. So we should expect roots to occur in pairs like this if we have complex numbers involved. Then the punchline is that these correspond to the functions e to the ax, cosine bx, e to the ax, sine of bx. And it's the same procedure that we have here. So this is what happens if our roots are complex. We get these types of functions showing up. All right. So we actually are in wonderful shape because we've talked about how do we handle different kinds of situations. How do you handle repeated roots? How do you handle complex roots? Yes, there seems to be an answer or a question.
I just thought of a question. So in the second part, C2 and then everything expanded, why is the cosine 3x positive?
So here, we're using the fact that cosine is an even function. So the question is, why is cosine 3x positive? Cosine of negative something is the same as cosine of positive something. Okay. And so we use the fact that cosine of negative 3ax and cosine of positive 3x are the same. All right, so in summary, here we go. Which really is just restating what we already have. But if we're given an nth order linear homogeneous differential equation with constant coefficients, okay, so that's, in other words, the nice kind, find that auxiliary polynomial, find the roots, and then you make the solutions by the following rules. If you have a real root and it's repeated, well, you just start, so this is the symbol gamma, e to the gamma x, and then you keep going as many times as you need. X, e to the gamma x, x squared, e to the gamma x, so forth and so on, until you get k of these. So essentially it says, look, real roots, e to the gamma x, and then bump up as you need. If you have complex roots, well, that's what we just talked about. So, alpha plus minus beta I. So it's e to the alpha x cosine beta x, e to the alpha x sine beta x. And you can have repeated complex roots. That can happen. And what do? The answer is you just do what you expect. You keep bumping up. So the next time that you have a set of pairs, you multiply by x. And if you have it again, x squared, and so forth and so on, until you have enough to account for all your pairs. And those are your functions. So now we understand how to handle the roots. So essentially, the only hard part, we'll put hard in quotes, because it definitely deserves the title, is finding the roots. Okay, so let's do a quick example. Write down the general form for a differential equation where the auxiliary polynomial has the following roots. So here, we don't even have the differential equation. What we've done is we've jumped ahead a couple steps. So normally we say differential equation, this auxiliary polynomial, and then the roots, and then we go to the general form. So we're just sort of saying, let's do the last step. And mostly this is saying, do we understand how to apply our rules? Okay, so we're just going to go through one root at a time and start building up our general form. So our first root, what does that give us as one of our functions? Gives us 1. So we have c1 times 1. What's our next root going to give us? It's x, right? Because we've already used 1. It's a repeated root, so we've got to bump up that root. So that says multiply by x. So c2 times x. Our next root. It'll be our next constant, c3, e to the x. What's our next one going to be? So the next root is negative 2. C4 e to negative 2x. Okay, our next one, which is negative 2 again. C5 what? X e to the negative 2x, because it's a repeated root, so we have to bump. Okay, our next root is a negative 2 yet again. C6 x what? X squared e negative 2x. Okay, now we're to our complex roots. 1 plus or minus I. What will that give us? Well, it gives us two functions. So which function do you want to handle first? The cosine or the sine? Cosine? Suppose it's the cosine first. What do we write down? E to the x. And then cosine x. C8 will be, well, we're still here because these come in pairs. Yeah, e to the x sine x. So yeah, remember that complex roots come in pairs. So the functions are going to come in pairs. Okay, how about our next one? Negative 3 plus minus 2i. So C9. E to the negative 3x. So the real part goes inside the exponential. And what else? Cosine 2x. The imaginary part goes inside the trig piece. Plus C10. E to the negative 3x. Sine of 2x. Okay, there's still Another one. Now, we had negative 3 plus minus 2i, and now we have negative 3 plus minus 2i again. This is repeated complex roots. We are allowed to repeat complex roots. So, we'll have another pair. C11?
Do we want to do next? Yeah.
X e to the negative 3x cosine 2x, because it's a repeated root, so you got to bump up. And finally, to bring it home, C12x e to the negative 3x sine of 2x. And there we go. That's it. So once we have the roots, the writing down the general form should be mechanical. Just a little bit of practice. Just remember, okay, do I have repeated roots? If I do, make sure to bump. If I don't, life is good. All right. Well, let's go in a different direction. This says, hey, let's suppose we get to something where we get the general form. Now we're going to go backwards. We're going to go back. Where it says, hey, I'm going to tell you what the general form is. You need to give me a differential equation. Now think about the process. Normally it's start with a differential equation, find that auxiliary polynomial, find the roots, write the general form. So we're reversing that. We're starting with the general form. So if we're starting with the general form, what should be our first step backwards? Talk about the roots. So let's talk about these roots. What root would have given us the function 1, which is the first piece? 0. What would have given us the function e to the x? 1. What would have given us x e to the x? 1. It's a repeated root of 1. Now, the e to the x cosine 4x and e to the x sine 4x, well, these come in pairs. So yeah, it's 1 plus or minus 4i. Okay, so now we've done one back step. So the next back step is to say, okay, what's the polynomial? Now before we do that, I'm just going to make a little side note over here where it says if you have a plus or minus bi, this is a root of the polynomial x minus a squared plus b squared. Now, if you don't believe me, you can check the process. This would say x minus a squared equals negative b squared. Take the square root of both sides. What would you have on the left? What would you have on the right? bi plus minus, because b squared becomes b. The square root of negative 1 gets you that I plus or minus. And then you add a to both sides. Okay. So let's talk about our polynomial. So 0 would be r. What would 1 be as a factor? R minus 1. Here, r minus 1. And 1 plus minus 4i, we can come over here. This would be r minus 1 squared plus 4 squared. All right, so let's go through here. If you square out r minus 1 squared plus 4 squared, can you do that? So r squared minus 2r, that's not too bad. Normally, if it's just r minus 1 squared, you should be able to say, oh, that's r squared minus 2r plus 1 plus 16 more makes plus 17. Now here, well, hey, we talked about r minus 1 squared. That's r squared minus 2r plus 1. Let's go ahead and multiply that by r. So we have r cubed minus 2r squared plus r from the first three pieces. Now, we have to keep going. What's the principle to help us finish here? Well, we want to keep expanding it all the way out. So we can say expanding. People like to use the word FOIL. Now, of course, FOIL means it stands for first, outer, inner, last, which is great if you have just 2 terms times 2 terms. Here we have 3 terms times 3 terms. So it's slightly more complicated. It's like, okay, first, first, middle, first, last. So it's no longer FOIL. It's but the principle of foiling is the key here. Principle of foiling says, pick something from the first and pick something from the last, and do it in all possible ways. That's the idea of foiling. So let's start. We'll start with r cubed. R cubed times r squared. R to the fifth. R cubed times minus 2r. Minus 2r to the fourth. R cubed times 17. 17r cubed. Now go to the next one. Minus 2r squared times r squared. Minus 2r to the fourth. Minus 2r squared times minus 2r. Plus 4r cubed. Minus 2r squared times 17. Minus 34r squared. So see, we did the middle term times each one of the three possible terms here. Now we start with r. R times r squared. R cubed. R times minus 2r. Minus 2r squared. R times 17. 17r. So you'll notice there's a total of 9 pieces here, which is what we should expect, because we had 3 things to choose from here, 3 things to choose from. 3 times 3 gives us 9. Add them up. How many r to the fifths do we have? Okay, so 1 r to the fifth. How many r to the fourths? Negative 4 r to the fourths. How many r cubes? 22 r cubed. How many 34s? Minus 36 r squared. How many r's? Plus 17r. Okay, so this is our auxiliary polynomial. One more step and we'll get back to our constant coefficient homogeneous linear differential equation. So, what is our differential equation? R to the fifth becomes, y fifth derivative. Minus 4, y fourth derivative. Plus 22, y third derivative. We can switch to triple prime now. Minus 36 times y double prime plus 17 y prime equals 0. And we got it. That's it. That's our differential equation. All right. One last topic. So, a second order Euler equation. So Euler is a mathematician. I know you might want to say, isn't that Euler? No, it's Euler. It's a differential equation that has the form ax squared y double prime plus bxy prime plus cy equals 0. Now, this is not constant coefficients because you have x's showing up. But notice that here, when there's no derivative, no x's. One derivative, one x. Two derivative, two x's. So it's like the power of x grows with the derivative. So that's what an Euler equation is. So if I had y triple prime, the third derivative of y, what would we multiply it by? X cubed. So that's an example. Now, there's a couple ways to solve this. One sort of way to think is, hey, try y equals x to the r and plug it in and try to find the roots for r. Because what happens is, every time I take a derivative, essentially I reduce the power by 1. See, if I reduce the power by 1, but I multiply by x to the 1, I get back to something that looks like x to the r. If I reduce the power twice, but I multiply by x squared, I'm back to x to the r. That's one way to do it. There's a second way, which is what we'll try to do in about a minute, which says, make a substitution. Let's change our variable, but we're not changing our y. We're going to change our input variable. So we'll introduce a new variable. We'll let v be natural log x. And what we want to do is translate. So we want to translate this into a differential equation involving y and v. So I have to say what happens to y prime and what happens to y double prime, because these involve x. See, y prime is secret code for dy dx. Well, to translate in terms of v, we say, well, you know, dy dx is the same as dy dv times dv dx. Why is this true?
Because dy over dx is how y changes when x changes. And if you want to relate y to v, then you can do how y changes as x changes times how x changes as v changes. Because they're proportional. So if you multiply these proportions together, you'll get the final proportion that you want.
Okay, so there's some notion of proportion. There's also another name for this is chain rule. Same ideas. So this is chain rule. What is the derivative of v with respect to x if v equals log x? 1 over x. Okay, so the hard part. So I'm just going to really fly through this one. If I want to take the second derivative with respect to x, it says take the derivative of the first derivative. But good news, we have the first derivative. It was just done. One line above. So it's really taking the derivative of y with respect to v times 1 over x. So we say, okay, so that says take the derivative with respect to x of dy dv times 1 over x plus dy dv times the derivative with respect to x of 1 over x. That's the product rule. Now, how do you take the derivative with respect to x of dy dv? Well, we do the chain rule again. That's really the derivative with respect to v of dy dv times dv dx times 1 over x. This is, I know. Hang in there. The punchline's coming. Derivative with respect to x of 1 over x is minus 1 over x squared. And so what we have is this second derivative of y with respect to v. dv dx is still 1 over x, so times 1 over x squared. And then minus dy dv times 1 over x squared. So here you go. Quick example in our remaining minus 2 minutes. X squared, y double prime, put in what y double prime is. You have d squared y dv squared times 1 over x squared minus dy dv times 1 over x squared minus 3x times y prime dy dv times 1 over x plus 4y equals 0. And what happens if we've lived a good, clean calculus life? Something beautiful happens here. The x's all cancel. So what you end up with, you have a second derivative of y with respect to v squared. Here you have a minus dy dv minus 3 dy dv, which is minus 4 dy dv plus 4y. And what kind of equation is this? Linear, homogeneous, constant coefficients, which means it's the kind that we like. We write down the auxiliary polynomial. We say, hey, that's r minus 2 squared. That means our roots are 2 and 2, which says that y has the form some constant times e to the 2v plus some constant v e to the 2v. Are we done? No, but we're darn close. What's left? V equals log x. So e to the 2 natural log x becomes what? X squared plus some constant log of x, x squared. Okay, so there's an example. And all right, we flew through that one. Sorry for going over. Hope you have a great day. See you next time.